backtrack rules. Where you are backtrack rules, you have backtracking. The second difference is the guard. The guard, okay, don't have to be flat. So guard can be any codes, yeah. And the third difference is, what is this third difference? The third difference, that's important. Okay, no freeze. No freeze, okay. In GHC, okay, if you have a call, you want to match the call against the head of a pattern. If there's no data ready, okay, it is a freeze. Okay, it is a freeze, you're waiting until data is available, okay. In here, there's no freeze, no laziness, okay. It's strict. If you don't have data you want to match, you don't have data, then you fail, okay. So, for efficiency rules, yeah. So, pattern matching rules, okay, for example, you have member check, X, okay, we have member check here. So, X is the same as the first argument, and then, okay, X is a member of the list, yeah. But if you call this predicate with this call, member, X, and the second one is a list, is a variable, okay, because this one doesn't match, okay, the second argument, so this one fails immediately. Okay, this is for, again, I said, for efficiency's purpose. And, well, matching rules is good, okay, it's good for efficiency, yeah, purpose. Why? Because the compiler can index all matching rules. Okay, actually, I can write a program, write a parser, for example, that can be arbitrarily faster than prolog. Okay, why? Because all the index arguments or all the input arguments are indexed. Yeah. And unification is still supported, but you have to write it explicitly. Yeah, as in here. Okay, so you say, oh, L is equal to this. Okay, this one contains X. Okay. All right, and also non-determinism. All right, this one is backtrackable. Yeah, so that's why this predicate, okay, becomes non-deterministic. Okay, it can return multiple answers. And well, in some cases, sometimes you have a large number of facts, and it's tedious, okay, to write all these facts as pattern matching rules. All right, okay, for that, well, Picat allows you to just have predicate facts, okay, and before you give a list of predicate facts, okay, you also declare how index declarations can tell the system how these facts are going to be indexed. Okay. All right, functions. So functions are not that special. What you do is you have a head, and then you have equal an expression. Okay, then this one becomes a function. Okay, so it is the same rule, but of course for functions you cannot use backtrackable rules. Okay, why? It doesn't make sense for a function to backtrack. Okay. So a function we know, okay, it is for each source there is only one sink, yeah, one image, yeah. So all rules in function definition must be deterministic. Okay. So in case the condition is true and the body is true, then you can just write the equation. Okay, this head equal expression. So here are several examples. Well, as you can see, okay, these programs are not that different from programs written in Haskell. Okay, but there are big differences. I mean, internally, first, okay, this is dynamically typed, so the compiler doesn't check types, yeah. And you can use list and array comprehensions as you can use list comprehensions in Haskell. And also, this is a strict language. Okay, that means before you make a call, all the arguments will be evaluated. Okay, it supports high-order functions, but okay, using high-order functions is not encouraged. Why? Because you pay a big price. It's not efficient. Okay, so you are encouraged to use list comprehensions, okay, when you want to use high-order functions. And well, patterns. Okay. Patterns in heads. are not allowed to have function calls. Well, since index notations, ranges, dot notations, and comprehensions are special functions, okay, they cannot occur in patterns. And you can use as patterns again. Okay, this was stolen from Pascal. Yeah? And the scripting, okay. Well, since this language, has loops, has all the ingredients, okay, you can write scripts as you do in Python. Actually, this is translated from a Python program, okay, almost as it is, yeah. So you want to write a script to draw this Pascal's triangle, okay. So, well, just two loops, yeah. Or you want to, for example, you want to write it in Prolog. Well, if you pen in the neck, it's too much, yeah. Here is another script which traverses directory. Yeah? So, this traverses dir, traverses a directory. The first argument is the depth, and the second one is the current directory. Okay, what do you do? Okay, since you deal with the directories, you need to import this OS module. Okay, you use this dir to retrieve all the files and the directories into a list. And then for each file in files, if file is not the current directory, and the file is not the parent directory, and then you get the full name, and then if it's a directory, they go down. Okay, you go down, okay, so you recurse on the directory, otherwise you print the file out. Okay, pretty straightforward. Alright, now let's do some exercise. Write a function that returns the number of zeros in a given simple list of numbers. Okay, well, there are many different ways to do it. Yeah? Well, actually, this is the simplest way to do it. Okay, in Picat, you can write a function, count zeros L, and equals, okay, sum 1. For each zero in L, you sum 1. Okay, actually, the compiler doesn't create a list of ones, and then, sum the ones up. The compiler, what the compiler does, it converts, okay, this into this tilde recursive program. Okay, so it runs faster, is concise, and runs faster. Okay, second exercise. Replicate the elements in a list a given number of times. So for example, you have replay AB, okay, you want to replicate each element 3 times, then you have A, B, B, B. How would you do it? Okay, so in here, okay, we can do it this way. Replicate L and N. So for each X in L, then I add X n times. Yeah, that's it, yeah. All right, let's consider this Google Code Jam problem. So give me a list of space-separated words, reverse the order of the words. Okay, here are test cases, and here are required output. So what we can do, okay, we can just write a program this way. Read a line to read a line, and use split two integer, change the string to integer. So this is a number of test cases. Okay, and for each test case, okay, what do we do? Okay, we use read line to read a line, okay, a string, and then use split to split the line into words. We get a list of words, and then we use reverse, and then use this join, okay, to produce another string, and then print it out. That's it. Yeah. Okay, it's very simple. Let's consider another Google Code Jam problem called store credit. So you are giving a list of items, yeah, list of items, okay, of this number 3, and also you are giving a credit. So you want to find 2 items, the indices of 2 items, okay, that sum up to the credit. Okay, so for example, okay, for this list, all right, so the expected output is 2, 3. Okay, 2, see, 75 plus 25. Okay, if you add them, you make 100. It's a pretty simple problem. All right, so we can do it in Picat this way. First, reading the number of test cases, T, and for each test case, okay, we read the store credit, and we read the number of items, And then we use an array comprehension to read all the items, all the prices. And then we use do case, we call do case. What do case does is, okay, uses this between. Okay, between is a non-deterministic predicate. Okay, so it searches for two indices, I and j. I over this range from 1 to the length of the sequence -1, and j over this sequence from I plus 1, okay, until here. And then check the condition, yeah? Okay, the sum of the two items, okay, is equal to the store credit, and then print it out. Done, okay? So it is called a generate and a test, yeah? Of course, okay, it is not so efficient because, you know, there are two loops involved. It takes in square time. So you can use a map, okay, and make it linear, yeah? Make it linear. What you do is for each item, you want to map, okay, to find all the indexes that have this. Okay, and then when you search, you don't want to search the entire list. You just want to search, okay, from the indices of this amount, yeah? Okay, then this one becomes linear, okay, it's much, very fast. That's the end of part 1. And second part, okay, is on combinatorial search with Picat. So first, let me talk about constraint programming in Picat. Okay, and then tabling for dynamic programming, and then planning. So first, Picat provides 3 solver modules: CP, set, and min. All these 3 solver modules follow the same API. Okay, so which makes switching from one solver to another seamlessly. Yeah. So, okay, this interface, okay, allows you to define domains of variables, restrict the domains of variables, okay, write arithmetic constraints, Boolean constraints, table constraints, and also global constraints. By the way, currently, global constraints are supported only by the CP and the set module, not the MIP module. And then you call solve to label variables. Here's the famous send more money example, yeah? All right. So send more money, you create variables, and then the domain, declare the domains, and then, okay, write the constraints, and then use solve, okay, to solve the variables. Okay, so in this example, import CP is used. If you want to switch to another solver, say set, okay, you just change the CP to set. That's it. That's all you need to do, yeah? Okay. Here's another example. Okay, so it's a Sudoku. Yeah, Sudoku is a game invented in Japan. Yeah. Okay, give me a board. Okay, a board where it's a two-dimensional array. A two-dimensional array. Okay, where if the entry is a field, then that's a number. Otherwise, it's a free variable. So what we do is we retrieve the variables. Okay, declare the domains of these variables, and then just write the constraints. Okay, so each row is different, each column is different, and each of these small squares contain different numbers. That's it. So you can see, okay, because of support of loops and support of data types. Okay, so Picat, becomes a wonderful modern language, okay, for constraint problems. Here is another puzzle, again invented in Japan. Yeah. Japanese are not just good at making cars, they are good at inventing puzzles too. So Numberlink, okay, the puzzle is giving several pairs of numbers. All right, you are required to find a path to connect, okay, the pairs. Okay, 1 with 1, 2 with 2, such that no paths can overlap each other. Yeah. So again, I know you cannot read this. Actually, I was sitting in behind, and the font is too small. You cannot read the font. By the way, I will make the slides available. Yeah.
You can read it here.
Yeah. Anyway, I will make the slides. Even if you can read it, I will make the slides available afterwards. Okay. All right. So the set is used. Actually, this set is amazingly efficient. Okay. So this is one of the instances used in answer set. Actually submitted to an ASP competition. This instance was not used because no solvers could solve it. Yeah. And there are so many pairs. Yeah, how many pairs? I don't know how many pairs. I don't want to solve it by hand. It's too much. Yeah. Okay, so it was solved by Picat using this slow computer in 150 seconds. So for some problems, the MIP is super. Yeah. So for example, this Maxflow problem. Yeah, MIP is outperforms other solvers. So that's constraint programming in Picat. Now let me switch to dynamic programming. Well, a very good example is this Fibonacci function, which generates Fibonacci numbers. Yeah. Okay. As you know, it's a beautiful definition. Yeah, using recursion. But unfortunately, if you run as it is, it's exponential. It takes exponential time. Okay. So in Picat, we just say table. All right, use table. Okay, then everything will be tabled. All function calls will be tabled, and all intermediate answers will be tabled. Okay, so the system, when the system sees a function call that has been, has been computed before, then it just retrieves the answer from the table. Okay, so then the program takes only linear time. Yeah. So, and some other features, actually, we made a lot of efforts in implementing this tabling system. Okay, it uses a mechanism called a linear tabling, which is, it's very simple and very, space efficient. And also, we use model-directed tabling for, optimization problems. And also, it supports term sharing. Okay, so if you have a component that is shared by multiple cores, then this component is tabled only once. Okay? And here is an interview question. How to compute this binomial coefficient? Of course, we know a formula. Yeah, we know a formula for this binomial coefficient. Yeah, but the interview, say we cannot use that formula. Why? Because because the computation overflows. Yeah. You use a factorial function, you will create a large number and then divide it by another large number. Yeah, you cannot use that formula. So, question: how are you going to compute this binomial coefficient? Yeah. Well, we have the recurrences here. So in Picat, you just define, write the recurrences and then say table. Okay, then it's done. It's faster. Okay, and so it doesn't overflow. Okay. All right, this is the general program for pathfinding problems. Okay, so give me a state. We want to find and a goal state. Yeah, we want to find a path that can transform the initial state to the goal state. Okay, so we can use this model-directed tabling. Okay, plus means it's input. Yeah, the state. Okay, the state is the input. Okay, the path is to be returned, so it's output. And also the length of the path is to be minimized, so it is min. Okay, so if the current state is already final state, then we don't need to go further. Just return empty plane, yeah, and zero cost. That's it. Otherwise, what do we do? Okay, we go to the next state by taking action, and then find a plane. Yeah. Okay. So this is this mimics the Dexter's algorithm for the shortest path problem. Okay, but we can use this for general pathfinding problems and also general planning problems actually. Okay, so this is the base for the planner. Okay, the planner is implemented by using tabling. Okay, so here is an example. Okay, this is the famous wolf, goat, cabbage, and there's nothing. Wolf, goat, farmer. Don't forget farmer. So farmer is a problem. Okay, so they are all on one side. Okay, this is a boat you can use to transport them to the other side. Yeah, each time only 2 items can take the boat. Okay, how? And also only the farmer can row the boat. Right? So how can you find a plan. All right, so we do this in Picat. Okay, in the beginning, all these 4 items are on the southern part of the river, and then we call best plan, yeah, to find a plan, to transform this state to a goal state. A goal state is all these, okay, all on the northern side of the river, yeah. And then for each one, we just write a rule. Okay, so farmer crosses the river with the wolf. Farmer crosses the river with the cabbage. Farmer crosses the river with the goat. Okay, 3 rules. Then done, yeah? And then just let the system search. So this planner is based on tabling. Okay, it allows use of structures to represent the states, which is very good. Yeah, unlike there's one for the PDDAO developed in the planning community. They don't allow you to use structures. Yeah. Sometimes you really need to think how to represent states. And also it supports domain knowledge and heuristics. Yeah, for example, if you know the rule is deterministic, yeah, you can make it deterministic to prompt search spaces. And you can use domain knowledge, yeah, domain knowledge. And also you can use heuristics, yeah, so like A star algorithm, not A star, iterative deep learning, yeah. So, so I'm here, I know, okay, the estimate cost from here to the goal state, I only have this amount of resource. I know I cannot reach the state, goal state. So what do? You don't go further, yeah? Okay, so what I do, I backtrack immediately, yeah? And there are, the planner provides several search predicates. Yes, so these are the search predicates. Okay, you can do unbounded search. Okay, you can do iterative deep learning search. You can also do branch and bound search. Okay, and also you can use heuristics. So during search, you can use this function to retrieve the current amount of resource, and then you can compare the amount with the heuristic value. Yeah. Okay. Okay. So let's say there's a 15 puzzle. How can we write a program to solve this problem? Right. So what do we do? Okay, so for this one, we can just use a list of positions. Okay, list of positions, yeah, for these tiles and this empty square. So let's say the first position is the position of the empty square. So it's row 1 and column 2. Yeah, you see the empty space is in row 1 and column 2. And then 1 is in row 2 and column 2. So 2. Okay, use this way. And then we have goal state. Then we define actions. Okay, so actually the program is very short. Yeah. All right, we define the rules. Okay, you can move the tile up, left, right, or down. Yeah, that's it. And you can also use the heuristics. Okay, there's a famous heuristic for this problem called the Manhattan distance. Yeah. Okay, so we compare the current resource. If the current resource is greater than the heuristic value, we proceed. Otherwise, we backtrack. Okay, so this is a slide. The slide is in the given direction. Yeah. Okay. All right. So and we use this. Okay, we use this. Well, it's pretty simple to write this Manhattan distance. So how about the performance? Well, it solves all the 15 puzzle instances. You want to use Prolog? Prolog? No, that's why in Prolog textbooks you don't see 15 puzzle. Okay, you see 8 puzzle. Yeah, you don't see 50 puzzle. Why? Because Prolog cannot solve this problem. Yeah. Okay, it's actually I will show you in the demo. Yeah, it solves these puzzles instantly. Yeah. And well, for if you use a better heuristic, you can solve 24 puzzles instances. Here's another example called the Ricochet Robots. This one is a very interesting game. Yeah. Actually, I know in Europe you can buy this game. I heard. Yeah. Okay. Ricochet Robots. You have robots on the board, and this location, which is a target location. Okay. One of the robots is called a target robot. Okay. So this red robot is a target robot. All right. The rules of the game. Okay. A robot can move, but once a robot starts moving, it will continue to move until it reaches a wall, or another robot, or obstacle. Okay. So for example, okay, this red robot decides to move in this direction. Then it has to move all the way until it reaches this grid, and then it stops. Okay. So this, okay, the goal of this game is how to move this, okay, target robot to this target location, following these rules. All right, we can use this state representation. So because this target robot is special, so okay, we represent it separately. Yeah. So for the target robot, okay, we have this argument. This is the current derived location, and this is the target location. And for other robots, okay, we store them as in a list. We don't distinguish them. Okay, we don't say blue, black, okay, or yellow. All of them are the same thing. So what do? We just ignore the colors and just use the locations. And then we have two rules. One rule is, okay, select the target robot to move. And then this one is select a different robot to move. That's it. Okay, so you can check online. Actually, I found a program written in C that has several thousand lines of code written by some guy at MIT. And still that program takes several hours because it does brute force search. Okay, how about this one? Again, this one takes less than 1 second, yeah, to solve US 16 by 16 sizes. Okay. So actually, it's not without effort. In the beginning, we tried to use Prolog. Okay, Prolog couldn't even solve 5 by 5 instances. Okay, so the good thing about this is because of tabling used. Okay. All right, so it is a little bit stunning, is it? Yes, actually. So in general, okay, this is a good language for solving planning problems. Of course, you need to cooperate. Okay, the tool has provided you with good, features, yeah. But you still need to use them appropriately in order to find the best, models. So you need to you need to find a good representation of states. Okay, what you need to do is, okay, leave out unimportant information. For example, for the Ricochet Robots, we just forget about the colors, of the robots, yeah, because they are not important for the planning. And also break symmetry, yeah, this is important. And find a good representation that is good for precondition checking and also state generation, and also facilitates term sharing. This is also important, term sharing, because in general, state space search, you have a large number of states, okay, but you have to table all the states, so you need to find a good data structure. Sometimes you need to use control knowledge to reduce non-determinism, okay, to make actions deterministic, and also to exploit dependent actions. And some other times you need to use heuristics. Okay. Good. So so it is only 1 hour. I think I'm going to finish early, so we can go to spa. All right. So not done yet. Not done yet. Okay. So I think I still need about 15 minutes. All right. So well, actually, during the past year, well, several people have written papers on Picat. There's a good sign. A good sign is, you see, I didn't write many papers. Most of these papers are written by other people. Yeah. So let me give you a highlight of these papers and also some of the web pages. So this is picatland.org is the page you want to start. Okay, so where you can download the system, including the C source code, yeah, and you can get the documentation, examples, and links to related websites. Okay. And actually, this is the second year. Picat was released 2 years ago, and last year, after the version 1.0 was released, somebody named Lucy Black wrote this blog titled "Is Logic Programming Making a Comeback?" Yeah,